All right, so we talk about the main idea behind block ciphers. Let's see some block cipher designs. So currently there are three main ways of designing a block cipher. One of them is substitution-permutation networks, called SPN. The second one is Feistel networks. These network words actually shouldn't confuse you. It is not about, network security or networks. This is completely something else. Of course, all books or lecture notes don't mention this, but nowadays many block ciphers are based on sponge functions. Okay. Actually, SHA-3 hash function is based on a sponge function. Current lightweight block cipher encryption standard is from NIST is ASCOM is also sponge function. So sponge functions are important. So I will give basic idea behind this, the fundamentals on all of three. Okay. So nowadays, most people actually design sponge function or permutation-based algorithms for encryption. Okay, so designing a huge algorithm sometimes confusing and hard to analyze. So what we do is design a round, okay, and repeat it many times. So this way it is easier to analyze and also implement. Okay, so we will be talking about rounds and talk about how many times they are repeated. Okay. So in all of these algorithms, as I mentioned, we have a secret key, and that is the only thing that we keep secret, right? So that secret key is used inside this algorithm, inside rounds. So how you use it actually depends on your design. So we call it a key schedule. So instead of using the key directly in every round, a key schedule algorithm is used to generate round keys from the secret key. Okay. So let me first talk about substitution-permutation networks, and you will understand the design principles here. So generally, it consists of three layers. Key addition combines the key material with the input. Substitution, this layer provides confusion. And a permutation layer, which provides diffusion. As you can see, the diffusion and confusion ideas are used here, and the key material is combined with the input. There are many block ciphers that are designed as SPN, like AES, Advanced Encryption Standard, or Present, which is a lightweight block cipher standard, IOS standard. Okay, so the main picture looks like this. So you have the plaintext block here, okay, and you are going to generate a ciphertext block here. So what you do is as follows: you have the secret key and put it into a key schedule algorithm, and you produce round keys, which are going to be used for every round. Okay. So you have the plaintext, you add round key to this plaintext, then apply substitution layer and permutation layer. So we call this one a round. Okay. In the second round, you do the same thing, but this time use the second round key, and so on and so forth. So as you can see, if we start with add rounds, at the end I have to add the round key again, because if you erase this part, permutation and substitution layers don't use the key material, right? So from the ciphertext, the person can go back. So here you are actually preventing them to go back. So think about it in this way. The person who listens to communication obtains the ciphertext. They know the algorithm, which algorithm we are using, but they don't know the key. So from ciphertext, in order for them to obtain the plaintext, they have to go backwards, right? But even the first step is adding the round key, but you don't know the round key. So from ciphertext, you cannot come here. So this means that you cannot obtain the intermediate values. So this way, you cannot go back to plaintext. Even if somebody captures a plaintext and the corresponding ciphertext, from these two information, you cannot obtain intermediate values and obtain the key from here if the cipher is designed in a good way. Okay, this is how you use an SPN. Okay, so what is inside this substitution and permutation layer actually determines which block cipher you are using. Okay, that is the whole idea. So for instance, in AES, for the permutation, we are going to use matrix multiplication. For present, we will be simply changing the places of bits, a permutation. Okay, so how you design these layers actually determines what kind of a cipher you design. So here's an example, for instance. So here I'm only focusing at a single round, okay, in the following picture. So this is a single round. This picture is the single round of present, which is ISO standard for lightweight block ciphers. So picture actually shows every layer, okay? So block size is 64 bits, okay? So there are 64 lines here to represent every bit, okay? Your key length can be 80 bits or 128 bits, although 80 bits nowadays does not provide enough security. But regardless of your key length, you have the key schedule algorithm which produces 64-bit round keys, okay? So when you have the plain text, first you XOR it with your first round key, okay? XOR operation is just addition modulo 2 for bits, okay? So after this layer, now this is the key addition layer, okay? Next layer, these S's are substitution layer, okay? So every 4 bit is fed inside to S box and 4-bit output is produced. So which 4-bit goes to which 4-bit actually represented is in this table in hexadecimal notation. So for instance, if all of the 4 bits are 0, in hexadecimal notation it is 0. So the output is C. C in integer notation is 12. But if you think that the rightmost bit is the least significant bit, when you write 12 as the bit notation, it becomes 1, 1, 0, 0. Okay, so this is the substitution. So here you are creating a confusion because the input was different. Now the output is completely different. So this is the layer you create a confusion. But as you can see, this confusion affects only these 4 bits, right? But I said that there should be a diffusion so that these changes affect other parts of the cipher. For this reason, in the permutation layer here, for instance, you are keeping this bit at the same place, but you are sending this bit to here, okay? Recall that this is a single round. In the second round, we will take this picture and put it below, so this bit will go here and go to S11 or something, okay? So this way, here you are performing key addition, here you are performing substitution, here you are performing permutation. A simple design. This is why it is for lightweight ciphers. But since we are working on bits, this is a good algorithm for hardware, but not good for software, right? Because in software, we are dealing with bytes. It is hard to, work on bits. I mean, not that hard, but it will consume a lot of CPU power just to even change the places of a few bits. So, but of course, there are different implementation techniques where you don't deal with these bits, but you can do some table-based implementation as well. But long story short, this cipher has number of runs as 31. So you take this picture, copy 31 times below it, and at the end, you add a final round key addition here, and you produce the ciphertext. So this is how a substitution permutation network works. So the person who obtains the ciphertext have to repeat all of the steps in a backward way. So in the forward direction, 0 goes to C for the S box. In the backward direction, you come from C and go to 0 and so on. Okay, a simple design. So
SPM'de hocam key stratejik algoritması sadece input olarak kim kullanıyor? Yani başka Cypher'dan blok kullanmıyor.
So a key schedule algorithm actually takes input as the key and then produces the key round key material. So it is to simplify the steps. I mean, if your key schedule depends on the input, then it becomes harder to analyze your key schedule because it will be input dependent, right? So this is why we try to divide the layers and try to analyze them independently. Because then you can look at the S box here and say if it is good or bad. For instance, by looking at this table, you might say that, okay, E goes to 1 and F goes to 2. But what if I replace these two, right? Write 2 here and 1 here. So will it be better or will it be worse? So this is the question. But in order to answer this, you should know how cryptanalysis works, okay? Maybe it will be more susceptible to differential attacks or not, depending on your changes, okay? So This is why designers choose it in a nice way. So in their mind, they always have the security, but they also have performance. Okay. Sometimes some S boxes will be easier to implement on hardware and so on. So you are trying to find the best place for security and performance. And at the end of the day, if you make a single change, then you are actually using a different cipher. So all of our analysis will not be applicable to here. So for this reason, we still receive a lot of academic papers where people make a small modification and then say that this is better, but they don't provide any security analysis. But all of the previous security analysis for this cipher actually may not be applicable to this new design. So if you are making a change, then you have to prove that you don't break any security. Okay. So second type is Feistel. It was introduced by Horst Feistel. A round of a Feistel network consists of a round function and a swap operation. Okay, idea is as follows. The B-bit input is divided into two halves. Round function is applied to one half and the output XOR to the other half. Key material is used inside the round function. Then the places of these halves are swapped. So let me try to show it with a picture. You have the plain text block, but now you divide it into two halves, right and left. So if you look at the right part comes and without any modification becomes the left part. Okay, but right part is also fed into a round function together with the round key, and the output is XORed with the left part, so left part is now modified. But left part becomes the right part in the second round. As you can see, this approach only modifies half of the input, then swaps the places of the half, so then in the second round modifies the second half. So this way it goes like this. At the end, generally, we don't do the swap operation because it doesn't provide any security, right? It is just a waste of operation. But here this has a good advantage because in the SPN ciphers, in order to decrypt, you need the inverses of these operations. For instance, in the encryption part, if you are performing a matrix multiplication, then in the decryption part, you have to multiply it with the inverse of the matrix, right? So you need to implement more, but this means that if you're implementing it on the hardware, you will be spending a lot of resources in terms of area, right? So in the Feistel, actually, you don't need the inverse of the round function. This might look counterintuitive, but look at the ciphertext and see how the person decrypts it. So you don't need to come here and go in this direction. So the arrows doesn't need to point the other way around. Actually, what you do is, you have the left part and the right part of the ciphertext, right? So this, you take the right part, you also feed it in the round function, obtain this one, so perform the XOR operation and obtain this part. So encryption and decryption are almost identical, right? But in the encryption case, here you are using the first round key. In the decryption part, you are using the last round key. So only the order of the round keys changes, okay? So this is why people generally prefer Feistel in hardware. In the past, this is why DES was a Feistel cipher, okay? So you can generalize this idea. Instead of left and right, you can actually divide it into 4 or maybe 8. This is a general picture of the Calaphia cipher. This is also ISO standard for lightweight block ciphers. The block size is 128 bits, so each arrows here represent 32 bits, okay? So now you have 4 lines, and you perform the similar operations like round function, round key, etc. Of course, how you design these F round functions determines the security of your cipher, okay? So there are some pros and cons. If you want to compare Feistel with SPN, pros are as follows. In the Feistel, encryption algorithm is identical to the decryption algorithm, as I just mentioned. Only the order of the round keys change, so it is easier to implement and provides, saves you the space on a hardware or your implementation cost. But SPN, a single round affects the whole input, so it's kind of you're producing more confusion and diffusion. Of course, depends on your choice of the primitives, but still, you are affecting the whole input. Cons is as follows. In the Feistel, a single round only affects half of the input. So for simple designs, you may need more rounds to provide enough confusion and diffusion. And in the SPN decryption procedure requires the inverses of the substitution and permutation layers, which might be, take a lot of space on hardware. But of course, you can turn your block cipher into a stream cipher depending on your mode of operation. So you don't always need to do this if you are using like a counter mode of operation and so on, which we are going to talk about when we talk about mode of operation. So I said that there are three general methods for constructing a block cipher. And third one, which not many people talk about, is the sponge construction. So Ascon won the NIST competition for authenticated encryption. So in this algorithm, we have a sponge function, and it is converted into a block cipher. So in the sponge function, its idea is as follows. So you have a huge internal state here, okay? Like here. It is 320 bits in Ascon, but it can be thousands of bits if it is not a lightweight cipher, okay? So you have a huge internal state, and you have a permutation, which also contains confusion and diffusion layers, which kind of mixes this internal state, okay? So initially you put IV, initialization vector, your secret key, and the nonce. Then perform this permutation operation 12 times. So internal state is changed. This is optional part. So now assume that you want to produce ciphertext, right? You want to encrypt something. So you take your plain text, for instance, in this case, a 64-bit. You have a 320-bit internal state, which is a lot larger than the plain text here. So actually, you take the plain text and XOR it with your top part of this internal state, just 32, 64 bits. And the result is produced as ciphertext, right? Now your plain text actually modified your internal state, but you also leak some information from your internal state by producing the ciphertext. For this reason, you mix the internal state again by performing some S-box operations, permutations, whatever you design. Then you produce the second block, and so on and so forth. Finally, you produce all of your ciphertext, and this CIs is your ciphertext. Okay. So we call the sponge function because here, as you can see, I mentioned that we have a huge internal state. And this part, when you want to produce output, you assume that you fill a sponge with water and then you squeeze it, so some water leaks, right? So here, this is what happens. This is the part where you squeeze the sponge and produce the water. Here we are producing ciphertext, okay? This is the main idea why we call them a sponge function. So very different design, but nowadays we have many algorithms, hash functions, block ciphers that are based on sponge functions like this. So idea is to keep the internal state large so that you provide security because you are leaking a small amount of data here. So here, as you can see, there are two variables, R and C. R is called rate because it depends how fast you are producing output, right? If R is 64 bits, your rate is 64 bits, but then this capacity determines your security because if you increase R a lot, then C decreases, and this actually might cause a security problem. So you are trying to find a sweet spot between R and C and so on. So we will talk about ASCON in the future. I actually will implement it in using the C programming language. So you will see how internal of this algorithm works. But this is an authenticated encryption algorithm. So we will talk about it when we talk about authenticated encryption. Yes, some design considerations for different platforms. So we are using encryption almost everywhere, especially with the IoT. We are using it in very, very small devices like 4-bit microcontrollers, devices with just a few bytes of memory and so on. So you have to keep in mind this kind of platforms to design your algorithm. But basic comparison can be done with hardware versus software. Here, I'm actually talking about hardware in general, like FPGAs versus CPUs, okay? So hardware implementations can easily work on bits. Since most programming languages focus on bytes, bit operations are more costly on software. Cipher design also determines the number of gates required to perform encryption on hardware or LUTs in FPGA or gate equivalents on ASICs. And this actually determines the area you need. But you don't have infinite area, right? For instance, in software, we are kind of free because our computers are really fast. We have gigabytes of memory. So generally, we don't care if we consume kilobytes of memory or more, okay? But if you are working on a small device, this is important. Code size is important for 8-bit microcontrollers and so on. But if you are working on a physical device, for instance, if you are building a smart card, actually you have limited place for encryption. So you cannot design a huge algorithm and try to put it on a smart card and then expect it to produce in a cheap way, okay? But since you are going to produce maybe millions of smart cards, even 1 cent cost, affects the whole price completely, right? So you have to need a good design that fits in the smallest devices. Code size or required memory is not a big problem for software implementations due to fast CPUs and large RAM, again, but it might be a problem for small devices like 4-bit or 8-bit microcontrollers. Another thing we need to consider is security versus speed. So speed is generally measured as throughput, so gigabits per second, megabits per second, depends on your platform and the speed. But adding more security measures, for instance, increasing the number of runs, increases the security but reduces the speed, right? Because if you design a cipher as 10 runs, then increases to 20 runs, now actually your speed is halved, right? Because you're doing the double thing. Or if you want to provide more confusion and diffusion, you may add more steps, and you may claim that this is more secure, but it will cause a slowdown. So aim is to find the best spot for security and speed. And ciphers performing well on hardware or software may not be suitable for constrained devices for RFID systems or sensor networks due to limited memory, battery, or computational power. Hence, we also need lightweight ciphers. So this is the thing. Nowadays, when we talk about, especially in IoT, you will see academic papers saying that modern ciphers are too huge to fit inside these small devices. So in the introduction, they say that for limited devices like with limited memory, CPU power, battery, and so on, we need small algorithms and so on. But then in the next chapter, they introduce a new design, but then perform the experiments on Raspberry Pi. So Raspberry Pi is not a not a limited device in terms of computational power or memory, because it is like a laptop, right? They have 4 gigabytes of memory, 4 cores or something. So they're not small devices. When we talk about small devices, we are really meaning small devices like 4-bit microcontrollers or devices with just 64 bytes of memory or that kind of stuff, okay? So lightweight ciphers, sometimes AES may not fit in a device because that's the capability of the device. But even if AES fits there, maybe you won't like the latency or throughput and so on. So for all this reason, we need lightweight ciphers, and it is a completely different topic. So let me finish with some standardizations. So ISO has many block ciphers as standards, but some of them are broken. And some of them support some short key lengths, like, for instance, present supports 2 key lengths, 80 and 120. But I always claim that 80 should be removed from the standards because people think that it provides long-term security, but actually not. If you have a lot of GPUs, you can actually perform a brute force attack on 80-bit present keys. At the NIST side, we actually have very limited of block ciphers. We had skipjack at some point, which is designed by NSA, by the way. If you're interested, you want to see how the mind of NSA works, it is a good algorithm to check. But it supports 80-bit security. So the key is 80 bits. So NIST doesn't allow anything less than 112-bit security. So skipjack is no longer used, but for legacy cases, you can use it. NIST also supports triple DES, which provides 112-bit security. So in this case, you repeat DES 3 times. But they said that they will remove it in 2024. Okay, so it is about to be lost soon because 2023 is about to end, right? So they actually only has a only standard called Advanced Encryption Standard, AES. But just recently this year at the February, ASCON won the lightweight competition. So NIST actually has two standards, AES and ASCON. So ASCON will be included in many IoT devices, many small devices in the future. So it is a nice area to, look if you are interested in writing a thesis or term project.